Mixture separations in fixed beds packed with morphs or zeolites are determined by three separate parameters. The most important one is the adsorption selectivity, determined from the thermodynamics of mixture adsorption. The second one is the severity of diffusional limitations, where D sub I is the intra-crystalline diffusivity of the guest component I, and R sub C is the radius of the crystallites of morphs or zeolites. If the ratio D sub I divided by RC squared is very large, there are no diffusional influences, and the separations are dictated primarily by the adsorption equilibrium. In addition, we have a third parameter, which is the ratio of the guest diffusivity within the pores for component 1 divided by the corresponding guest diffusivity for component 2. Let's call that the diffusion selectivity. We can identify two scenarios where for components 1 and 2, both the adsorption selectivity and the diffusion selectivity are greater than unity, and we have synergy between adsorption and diffusion. Another scenario is one in which the adsorption selectivity is greater than unity, but the diffusion selectivity is significantly lower than unity, and this diffusion selectivity serves to override the adsorption selectivity, and we have antisynergy. All these discussions are based on my paper published in Precision Chemistry and online in 2023. Let's pick up some of the highlights from my paper in the subsequent slides. The experimental data on the transient breakthroughs for 1090 propene mixtures in a fixed bed of CYP6 copper TPA, as reported in this chemical science paper, is shown here with these red circles. Transient breakthrough simulations, ignoring diffusional influences, are shown by the continuous solid black lines here. We note that the experimental data on the transient breakthroughs show that the productivity of purified propene is larger in the experiments than anticipated by a model in which diffusional influences are considered to be of negligible importance. The conclusion to be drawn by this comparison of transient breakthrough simulations without diffusional limitations and experimental data would lead us to conclude that there is synergy between adsorption and diffusion, and this synergy is described in detail in this publication. To illustrate the importance of the synergistic influence of intracrystalline diffusion, I show here a comparison of two types of breakthrough simulations. The one in black is the same as the one shown here. Here, the intra-crystalline diffusional influences are considered to be of negligible importance, and the breakthroughs are sharp. The simulations in red are simulations in which we have a diffusional selectivity of 5 in favor of propyne, and the severity of diffusional influences for components 1 and 2 are described by these two parameters. Due to the synergy between adsorption and diffusion, the gap between the breakthroughs of propene and propyne is wider than in the simulations in which intracrystalline diffusion influences are considered to be negligible. The net result is that the synergistic influence of diffusion would lead to a higher productivity of the desired propene product that is recovered at the exit of the fixed bed adsorber during the adsorption cycle. Recover ethine from mixtures with carbon dioxide, it is preferable to use metal organic frameworks that selectively adsorb CO2. In a recent paper published in Separation and Purification Technology 2023, experimental data on transient breakthroughs with the morph Y BPTC are reported. These are shown in red here. An important feature of this morph is that both adsorption and diffusion favor CO2. I compare here the breakthrough experiments with breakthrough simulations in which diffusional influences are completely ignored. The breakthrough simulations are described in my paper in Precision Chemistry 2023, and if we compare the breakthroughs, we note that the experiments show that C2H2 breaks through earlier and CO2 breaks through later than anticipated in the simulations in which diffusional influences are neglected. Consequently, the productivity of purified ethine is higher in the experiments than in the simulations ignoring diffusion. The productivity values are 1.05 moles per kilogram for a model in which diffusion is ignored, and in the experiments, a C2H2 productivity of 1.52 moles per kilogram is achievable. This demonstrates the significant increase in productivity due to synergy between mixture adsorption equilibrium and intracrystalline diffusion. With YBPTC, both these phenomena favor CO2. The separation of mixtures of CO2 and C2H6 is relevant in the context of natural gas processing. Current technologies for CO2 C2H6 separations use extractive distillation because of azeotrope formation. In my presentation today, I'm going to discuss a different strategy for separating mixtures of CO2 from C2H6, And this strategy relies on anti-synergy between mixture adsorption and diffusion in microporous crystalline materials. In particular, I'd like to consider separations using DDR zeolite that consists of cages separated by narrow windows with an aperture size 3.65 angstrom. The shortest aperture distance, and the longest distance is 4.37 angstrom. Both of these gas molecules jump lengthwise across the windows, and since the cross-sectional dimension of CO2 is smaller than that of C2H6, the mobility or diffusivity of CO2 is significantly higher than that of C2H6. Let's look at experimental data on transient uptake within crystals of DDR zeolite. The experimental data are shown by the symbols. The red circles are for CO2, and the blue squares are for the uptake of C2H6. At equilibrium, the loading of C2H6 is significantly larger than that of CO2. However, if you look at the initial transients, we note that the CO2 loading within the DDR crystals is significantly higher. This is because of the higher mobility of CO2. The pores are initially filled with CO2 before they reduce in the loading to reach the equilibrium value. So there is an overshoot in the CO2 loading during the initial transients. To model these experiments, we resort to the Maxwell-Stefan diffusion equations, and the expression to describe the transient uptake of the component loadings is described by this partial differential equation, where Qi is the molar loading of component I at any position R within the crystallite, which is assumed to be spherical, at any time t. This time derivative is related to the molar flux of species I, and the molar fluxes are described by the Maxwell-Stefan diffusion equations as being proportional to the gradient of the chemical potential of species I, and the proportionality constant is the Maxwell-Stefan diffusivity d sub I. Rho is the framework density of DDR. The experimental data can be matched taking the ratio D1 divided by D2, the ratio of the Maxwell-Stefan diffusivity of CO2 to the C2H6 to be 1333. And there is another parameter that is important, and that is the ratio of the Maxwell-Stefan diffusivity for component 1, which is CO2, divided by the square of the radius of the crystallite. And to match the experiments, we take the diffusional time constant to be 0.125 per second. I'll return to these parameters later in my presentation. So the mixture adsorption equilibrium favors C2H6, but the diffusion selectivity favors CO2, and we would like to cash in on the anti-synergy between adsorption and diffusion to achieve the separation of CO2 C2H6 mixtures in fixed bed adsorbers. For a feed mixture, say 50-50 CO2 C2H6, we would like to recover purified C2H6 in the adsorption phase. In other words, we would like the pores to selectively take up the more mobile component. So we need to achieve or realize kinetic separations. I consider transient breakthroughs in an adsorber packed with a DDR zeolite. The feed mixture consists of an equimolar mixture of CO2 and C2H6 with partial pressures 20 pascals each, and the breakthrough simulations have been carried out for two sets of conditions. The two scenarios are shown here. The blue lines are the scenarios in which the diffusional time constant d1 divided by rc squared is 1.25 times 10 minus 3. The continuous blue line is for the breakthrough of C2H6, and the dashed blue line is for the breakthrough of CO2. So if we have strong diffusional limitation that is characterized by small values of this diffusional time constant, the component that breaks through first is C2H6. So this is the desirable scenario where we have kinetic separations dictated by diffusion that favors CO2, and CO2 is preferentially adsorbed. If, on the other hand, the diffusional time constant is significantly larger, say 0.5 per second, the breakthroughs are shown by the black lines. The continuous black line is for C2H6, and the dashed black line is for CO2. In this case, CO2 is the component that breaks through earlier. This is not a scenario that is desirable because we would like to have purified C2H6 leaving the adsorption cycle. So the message here is that for kinetically driven separations, we need to use crystallite sizes that are large enough to lead to significant diffusional influences. And in this set of calculations, they need to be lower in value than say those used in the uptake experiments. Watch also my presentation on what drives kinetic separations on my YouTube channel that discusses further details of the modeling of these breakthroughs for kinetic separations. All the modeling details are available in my publication in ACS Omega, published in 2019. The separation of alkane isomers is of great importance in the petroleum industry. If we look at the isomers of C5, C6, and C7 alkanes, we note that for C5 alkanes there are 3 isomers: normal pentane, 2-methylbutane, 2,2-dimethylpropane, or otherwise called neopentane. The boiling points are shown here, and we see that there is a difference of about 20 degrees in the boiling points. But if you look at the research octane numbers, we note that the branched isomers have significantly higher research octane number than normal pentane. The same is true for the isomers of hexane and heptane. The branched isomers have higher octane numbers than the linear ones. And if we examine more closely, we note that the di-branched isomers have higher octane numbers than the monobranched isomers. This is true for the isomers of hexane and also for heptane. The di-branched isomers are preferred components for incorporation into the gasoline pool. Therefore, there is an industrial need to separate the isomers of C5, C6, and C7 alkane to yield three different fractions: linear, monobranched, and di-branched. And the di-branched isomers are the preferred components to be separated and incorporated into the gasoline pool. And the question is, how do we separate the di-branched isomers from the monobranched isomers, and how do we separate the monobranched isomers from the linear isomers? And if we look at the boiling points of C6 and C7, we note that the differences are quite small. It's possible perhaps to separate the linear from the branched ones, but the separation of the di-branched isomers from the linear isomers is a difficult task. And that is the topic for discussion in my presentation today. I show here a process flow scheme for the alkane isomerization process, in which a feed mixture consisting of C5, C6, and C7 alkanes is fed to the isomerization reactor that is catalyzed by Mortonite catalyst. The products emerging from the isomerization reactor is a thermodynamic equilibrium of the isomers of C5 alkanes, C6 alkanes, and C7 alkanes. In the separation step, LTA5A zeolite is used in order to separate the linear isomers NC5, NC6, and NC7 that can pass through the narrow windows, typically of diameter 4 angstrom, 5 angstrom, and the bulkier monobranched and dibranched isomers are unable to hop from one cage to the adjacent cage, and they are recovered in the raffinate phase. The linear isomers can be recycled back to the alkane isomerization reactor. For background on the process details, I refer you to my 2 papers listed here. An improved process flow scheme would be to use MFI zeolite as an adsorbent in the separation unit. And the advantage of using the MFI adsorbent is that we can separate the di-branched isomers from the linear isomers and monobranched isomers, and the linear and monobranched isomers can be recycled back to the isomerization reactor, whereas the di-branched isomers that have significantly higher research octane numbers can be directed and incorporated into the gasoline pool. I refer you to my publication in Physical Chemistry and Chemical Physics, published in 2015. Also, see my presentation on entropic separations on my YouTube channel. I focus now on the separation with MFI adsorbent. MFI zeolite is a suitable adsorbent for separating alkane isomers. MFI stands for mobile 5. It has a set of intersecting channels of 5.5 angstrom. These are the straight channels, and in this direction we have the zigzag channels. These channels intersect at these locations, and there are 4 intersection sites per unit cell. The branched isomers of alkanes, say 2-methylbutane, 2-methylpentane, and 2,2-dimethylbutane, all the branched isomers prefer to locate at the intersection sites where it has more leg room. This is shown by the computational snapshots here. There are 4 intersection sites per unit cell, and the saturation capacities of the unary isotherms for these 3 isomers are all 4 molecules per unit cell. For 2-methylbutane, the Langmuir constant is 4.12 times 10 to the minus 5 Pascal minus 1. The corresponding Langmuir constant for 2,2-dimethylbutane is higher. It's 7.12 times 10 minus 5. And the Langmuir constant for 2-methylpentane is even higher than that of 2-methylbutane because of improved van der Waals interactions with the channel walls, and the Langmuir constant is 1.27 times 10 minus 4 Pascal minus 1. However, the diffusional time constants are shown here. These were determined experimentally, and these diffusional time constants are the highest for 2-methylbutane. This lowered slightly for 2-methylpentane, and the lowest diffusional time constant is for 2,2-dimethylbutane. Therefore, within the intersecting channels of MFI zeolite, 2-methylpentane has the highest adsorption strengths, but the dibranched 2,2-dimethylbutane has the lowest diffusivity. Let's examine how adsorption strengths and guest mobility play out against each other. And I demonstrate this by examining a set of 6 experiments reported by Joly-Maitre in the AICHE journal paper published in 2002. The analysis I will be presenting is based on my own paper published in ACS Omega in 2019. In these 6 figures, A, B, C, D, E, F, I plot the experimental data of Joly-Maitre as published in the AICHE journal in 2002. The experimental data are shown by the symbols. These 2 experiments here are for binary mixtures of 2-methylpentane and 2,2-dimethylbutane. The experiments show that the component to elute first is 2,2-dimethyl butane that has the lower adsorption strength and also the lower intracrystalline diffusivity as compared to 2-methyl pentane that has a higher adsorption strength and also a higher diffusion coefficient. The continuous solid lines are the breakthrough simulations ignoring diffusional influences, and we note that the match is poor because diffusional influences are strong. Diffusional influences make 2,2-dimethyl butane elute the adsorber earlier than anticipated by a model that ignores intracrystalline diffusional influences. Indeed, diffusional influences are helpful in the separations because there is a wider gap between the breakthrough times from experiments than those anticipated by a model that ignores diffusional influences. Put another way, adsorption and diffusion act synergistically in runs 17 and 18. The partial pressures indicated here are the partial pressures of the feed mixture at the inlet to the fixed bed adsorber packed with MFI pellets. The experiments shown here, these four set experiments run 19, 20, 21 and 22 for ternary mixtures of 2-methyl butane, 2-methyl pentane and 2,2-dimethyl butane. In all four experiments, the component to elute first is 2,2-dimethyl butane that has the lowest mobility within the intersecting channels of MFI zeolite. The component to elute last in all four experiments is 2-methyl pentane that has the highest adsorption strengths of the three components. What is interesting to note is that the simulations in which diffusional influences are considered to be of negligible importance, the component to elute first is 2-methyl butane, but this is not in agreement with the experiments because in the experiments 2,2-dimethyl butane elutes first. This reversal in the order of breakthroughs of 2-methyl butane and 2,2-dimethyl butane is purely ascribable to the significant differences in intracrystalline diffusion due to the significantly lower mobility of 2,2-dimethyl butane within MFI zeolite. 2,2-DMB elutes first. So diffusion overrides the hierarchy of adsorption. And this is also helpful in the separations because we want to recover 2,2-dimethyl butane for incorporation into the gasoline pool, and due to diffusional influences, the component to elute first and recovered in the raffinate phase is 2,2-dimethyl butane. So diffusional influences help separations. Let us demonstrate that quantitatively in the next slide. To model the breakthrough experiments published by Joly-Maitre, we need to take proper account of both adsorption and diffusion And for modeling of diffusion inside the micropores, there is a need to incorporate the Maxwell-Stefan diffusional formulation, in which due account is taken of thermodynamic coupling effects. And I explained this in my 2019 paper published in ACS Omega. Watch also my YouTube presentation, Diffusion and Micropores. And there are other presentations on diffusional effects in zeolites and morphs that can be viewed on my YouTube channel. The set of 6 experiments can be reproduced nearly quantitatively by a model in which due account is taken of the interplay between adsorption and diffusion using the Maxwell-Stefan diffusional formulation, and the predictions of the breakthroughs are shown here by the continuous black lines. For all 6 experiments, there is one-to-one correspondence between experiments and simulations. So I conclude by saying that MFI zeolite is suitable for use in separation of alkane isomers. The separations are synergistic in nature because the diffusional influences serve to enhance the separations that is dictated by mixture adsorption equilibrium. And in my reckoning, MFI zeolite is the most suitable adsorbent for alkane isomer separations. To model the breakthrough experiments published by Joly-Maitre, we need to take proper account of both adsorption and diffusion. And for modeling of diffusion inside the micropores, there is a need to incorporate the Maxwell-Stefan diffusional formulation, in which due account is taken of thermodynamic coupling effects. And I explained this in my 2019 paper published in ACS Omega. Watch also my YouTube presentation, Diffusion and Micropores. And there are other presentations on diffusional effects in zeolites and morphs that can be viewed on my YouTube channel. The set of 6 experiments can be reproduced nearly quantitatively by a model in which due account is taken of the interplay between adsorption and diffusion using the Maxwell-Stefan diffusional formulation, and the predictions of the breakthroughs are shown here by the continuous black lines. For all 6 experiments, there is one-to-one correspondence between experiments and simulations. So I conclude by saying that MFI zeolite is suitable for use in separation of alkane isomers. The separations are synergistic in nature because the diffusional influences serve to enhance the separations that is dictated by mixture adsorption equilibrium. And in my reckoning, MFI zeolite is the most suitable adsorbent for alkane isomer separations.